All right, everybody. Round of applause for Denise with Intro to Test-Driven Development and Go.
Thanks, everyone. I'm really happy to be at the first ever Gocon Canada, so that's very exciting. My name's Denise. This is the Introduction to Test-Driven Development in Go. I drew those Psyducks. Come on. Okay, so by way of introduction, my name's Denise. I saw some of you at DevOps Days earlier this week. I was also speaking there 2 days ago. I work as a senior software engineer at Pivotal. I'm on the Concourse team. Topher was on the team until very shortly. He made sure to leave Pivotal right as I joined Concourse, so thanks, Topher. No, just kidding. So he already talked about what Concourse is, so I'm not going to cover that part. I really like cats. Hopefully that will become evident as I go through my slides. And when I'm not up here talking about things like TDD, I like to use art to break down technical concepts, and I'll show you an example of that. So a few months ago, I drew this sketch note on what Istio is, because I had to learn what a service mesh was. So I was like, I'm just going to draw this thing so that everyone can learn what a service mesh is. So anyway, I have stuff like this and other things all on my website, which is at deniseyu.io/art. Unless media in this talk is attributed or copyrighted, I drew everything. And people often ask me, hey, I really like that Istio drawing. Can I use it in my own blog post? And the answer is yes, please do. You don't need to ask me. My usage policy is on my website. I want you to use my stuff freely. If you want to make money off of it, ask me first. But other than that, all good. So just sort of to lay the foundation for this talk, this is not a Golang 101 talk. The examples I use are, I try to make the examples as simple as possible, but I am going to work with some basic assumption that you've seen Golang before, you've written a little Golang before. This is a TDD 101 talk, though. I'm going to assume no previous experience with test-driven development. If you've used it before, hopefully you'll learn some new things. If you've never used it before, hopefully you'll leave this talk with some new tools in your toolbox. So here's what I'm going to cover today. What is test-driven development? How do I use it? How does it help me? Why should I learn this thing? And I'm going to close with a discussion of how TDD, when you start using it as part of your software development process, can actually lead to improved software design overall, which I think is the coolest side effect. So part one, what is test-driven development? This picture was when my friend Steve asked me to draw a picture of trunk-based development. So test-driven development is a software development practice that uses automated testing in order to create short feedback loops that guide us in the development of source code. So what do I mean by these short feedback loops? When you talk to people about TDD, they'll usually say this one thing over and over again: red-green refactor. So this is the sort of the core principle of test-driven development. What this means is we start with the red state. Some testing tools actually do output like red text of the terminal, which is kind of, I don't know, nice if you're a visual person like me. But red just means we write a test first and we make sure that it's failing. If you're not starting from a failing state, if your tests are magically passing, then you might not be getting the level of verifiability that we actually want. So once we establish that our tests are failing, we move to green. We change the source code just enough so that the test is passing. And of course, we try to keep all the other tests passing as well. And the final part, and I think the most important part, is to refactor. So that means to take an extra minute to just look over the code that we've written, look over both the tests and the code that we've written, and ask ourselves, is there anything that could be named better? Is there anything that could be grouped better? Is there anything that any duplication that I can remove? Things like that. So what are the types of tests that we can write? The testing pyramid is a device that lots and lots of testers will tell you about. I think it's a fantastic device for thinking about how to invest testing effort. So what do I mean by that? This is a framework. So at the bottom of the testing pyramid, kind of like the food pyramid, right? Like the foundation of the testing pyramid is unit tests. So unit tests cover a very small piece of code in each test, hopefully. They should be runnable offline. They should be fast to develop. They should be fast to run. And they should be small in terms of their coverage. And then further up, you can have integration tests, which are tests that assert the interaction between more than one unit. And of course, at the top of the stack, you can have fancy end-to-end tests, maybe that write actual rows into databases, whatever it is. End-to-end tests should be slow, they should be expensive to run and expensive to develop. So the testing pyramid suggests that, of course, unit testing should be your foundation. So I think what that means is that if you don't want to do testing, if you have no tests whatsoever, at the bare minimum, you should think about having some unit tests. So you can use TDD to create feedback loops at any layer of this stack, but the examples that I'm going to be using today are unit tests. So that brings us to part 2. How do I use this thing called test-driven development in Go? Hopefully some of you in the room are starting to be TDD converts and thinking, okay, this, maybe I can get behind this TDD thing. So the thing that I love about Golang, and I think the reason why all of us are here, is because Golang is super developer friendly. Like, they've really, really thought a lot about developer-facing tools, and I think the core testing library is no exception to that. So all of my examples today are going to be using, most of my examples are going to be using GoTest, which is the lightweight test runner that just ships with Go. You don't need to install anything extra to use it. At the end of this section, I'll show you a side-by-side example of a Go test assertion and an assertion that does the same thing but uses a couple of third-party libraries if you're used to richer syntax, maybe if you come from like Java or Ruby. So we're going to go through a very, very simple example. We're going to use the red-green refactor workflow, and I'm going to try to be super, super disciplined about it. It's going to feel slow. It might feel a little bit clunky, but I promise that this is actually the workflow that at least I use when I'm working in a domain that I'm not 100% confident in. So let's say I've never written Hello World before. This is like brand new for me. Imagine we have a business requirement that we need to implement some logic that greets whoever it is that comes to our website. So we can start by writing a test like this. So we pull in the testing package, we assign 2 strings, the value that we actually got and the value that we expected to get, and we just compare those 2 strings. If they don't match, we use the testing library to throw an error. And in this case, we are designing the error message to print out both the value that we got and the value that we expected. So what will happen, so to run this, all you need to type into the command line is go test from within the package directory. So what will happen when we run this test? Well, right now it's not going to compile because we've never defined hello. So let's follow the error message. So a really key part of TDD is even if you can see 2 steps ahead, it's still worth developing the muscles to only move 1 step at a time. So in this case, we're just going to try to change this error message and make that compilation error go away. So we can do something like this. We can implement the function, we can satisfy the expected type interface, or type signature, and what I like to do is just return the 0 value of the return type. So in this case, we're just going to return an empty string. And when we run go test now, the compilation error will go away, and now we're actually seeing the error message that we designed. So we're still at red, of course. So let's write the minimum amount of source code so that we can get to green. So in this case, a long time ago when someone was teaching me TDD, they said, oh, you can slime it. I was like, what does that mean? Like, well, just hard code whatever it is that makes the test green. Slime it. I was like, okay, that feels dirty. And I was like, yeah, slime it. I was like, okay, well, I'm going to use the word sliming from now on to think about this. So slime the test, like make it pass in the dirtiest, like ham-fisted way possible. In this case, just hard code the string and don't do anything with the input. So if we run it, it's going to pass. We slimed it. We're at green. But there are some problems with this implementation, right? Like, this isn't going to be production scale. It's not really going to work if anyone whose name is not Gocon visits the website. So our source code doesn't actually do anything with the input. You can probably have an idea of where we're heading, but let's be really disciplined about the TDD process again, and let's use tests to force evolution in the source code. But of course, now that we're at green, before we jump back to red, let's take some time to refactor. Let's take a moment to see if there's anything that we can clean up. So the source code right now is pretty simple. It literally is just return hello Gocon. So we're not going to worry about that too much. But let's take a look at the tests. So maybe since we know we're heading towards multiple test cases for the same function, we can introduce test groupings. So the core testing library gives you t.run for this. You can also just write another top-level function assertion. Personal preference is I like to have the functions be the top, and I know in this case I did it wrong because it says test hello world when it should say test hello. But different inputs can be, I prefer to have those be different describe blocks or different run blocks. So this will give us a logical place for the next test that we write to live. So I truncated the top of the test file a little bit so the text could be bigger. So we'll write a second test that says, hello to Zach. And of course, when we run this test, we would expect the hello Zach test to fail because we've hard-coded it to say, hello Gocon. So we're back at red, which means now we can start amending the source code. So if we update the source code to actually interpolate, or I guess like, that's not really string interpolation, it's like munch the strings together, I don't know what that's called, and take the input string, now we have production code. This is web scale. So we can run go tests, and both tests are passing at this point. And since we're back at green, it means that we should also take another moment to see if there's anything we can refactor. So I think, again, source code is fairly straightforward, but let's take a closer look at our test code. So a really, really common problem I see when people start getting started with TDD is that once you write a test, people never want to delete their tests. They're like, no, I put like my effort and my time into writing that test, I've committed it, I wrote the best commit message, it's gonna be there forever. But here's the thing, like, this is a toy example, and it takes almost no time to run. But in a real system where you have dozens of tests or hundreds of tests, if you have too much coverage on the same code path, that actually does increase the amount of feedback time your developers have to wait before they can move on and think about the next problem. So there is a cost in terms of context switching, in terms of development cycles to having tests that don't do anything. So in this particular case, I think the way that, at least like, we can sort of reason that, okay, Gocon is a non-empty string, Zach is a non-empty string. These are both probably pretty similar cases. There's no indication that the string Gocon would behave differently from the string Zach. So these are both the same happy path. We probably don't need both of these tests. So let's thank one of these tests for their service and get rid of it. It was good that we went through the process of writing these, because these tests forced us to evolve the source code. But we don't always need to keep all the tests around forever. So our final test suite might look something like this. I arbitrarily chose to delete the Zach test. You could also delete the Gocon test. It doesn't actually matter. So I want to close out this section by just, if you're not using GoTest in your workflow right now, if you're not using TDD, like, that's fine, but I really think you should at least take a look at GoTest because it ships with some really, really interesting tools. You get benchmarking for free right now. You get test coverage checking for free. If you're writing a lot of Go routines, you get race condition identification for free. And you get tons and tons of other things. Just type GoTest -- help into a terminal. You don't even need to use the whole TDD workflow to benefit from these tools. Again, like, one of the many reasons why I think Go is such a developer-friendly language, I would definitely encourage you to take advantage of the things that this library already gives you for free if you're not doing that. So I promised earlier to the Ruby and Java people in the room, so if your programming background is in something like Ruby, or maybe something like, even JavaScript these days comes with a lot of matchers, like fancy stuff, like compare this array to that array. So you might find it a bit tedious to write your own, like, if this doesn't equal that all the time. First of all, welcome to Golang. If error doesn't equal nil, then like, that's your whole life. But there are a lot of extension tools out there that can help you make your Go testing frameworks feel a little bit more like what you're used to. So at Pivotal, we use a test runner library called Ginkgo, and we use a matcher library called Gomega. So these two tests do exactly the same thing, but you can tell that the one on the right-hand side feels a little bit more like JUnit, feels a little bit more like RSpec maybe. But of course, like, the caveat with using libraries is that they introduce magic, and you run the risk of spending time debugging the test suite rather than, I don't know, fulfilling business requirements or whatever it is. So to recap this section, the TDD basics are go really, really slow, stick to red-green refactor, move incrementally, change your code only when you're guided by an error message, use failing tests to drive out new behavior, be really careful about writing tests that magically pass, and of course, don't forget to refactor. Definitely spend that extra beat to clean up both your source code and your tests, and then you'll close the loop on that. So some of you might be wondering now, okay, well, that sounds great, but I don't want to like spend my whole life fixing compilation errors. Like, how can TDD actually help me as a software developer? So I have a couple of ideas here, and this is both from me talking to my friends that use TDD at their jobs and also from personal experience. So the first, I'll let the GIF play. So one of the benefits of having the artifacts that TDD gives you, so TDD gives you a test suite, and that's your baseline. So when you're developing new features, like we're all human, we make mistakes, we might introduce regressions. Having a baseline of tests that assert the fundamental behavior of your program helps you prevent regressions. It's just one layer of like basic tests that's really cheap and fast to run. A failing test is always going to be faster than having a QA person or a customer discover it in your production environment. So this is something I'll talk about a little bit more in depth later on, but a lot of testing patterns and a lot of the things that writing code that's testable drives out leads to code that's more modular, and it leads to code that has stronger boundaries. So the good thing about this is if you have modular design, it means that you can take a big nebulous business problem and represent it as small decomposed units that humans can reason about more effectively, and that the humans can extend or deprecate in the future. So another reason is that when you write tests, another benefit of having the artifact is that you actually get developer-facing documentation for free. So of course, you can always have written documentation. You can have READMEs, you can have like usage documentation, you can have runbooks, you can even have code comments, you can like do all this stuff. But the nature of static documentation is that it takes effort to keep it up to date. You have to really invest in process change to prevent drift between the documentation and the source code. So when you're using unit testing, or when you're using like any kind of runnable tests as an extra layer of documentation, like you can make your describe blocks have strings that are really, really intention revealing about what the test case does. You leverage the fact that it's all runnable code, like we're all developers, we can read code. They won't drift as frequently. When they do drift, your pipelines will fail. But I think the most important reason is one that I'm going to explain using a quick anecdote. Does anyone remember this game? Did anyone play this game back in the day? Okay, I see some nods. This was the first Crash Bandicoot game for PlayStation, and it came out in like 1997. I used to play this in my cousin's house all the time. So for those of you who are familiar with this game, you might remember that this game had a bizarro save mechanism. So back in these days, you couldn't just auto-save your game, because saving a snapshot of the world is a really expensive operation, and you only had like that much CPU or memory. So a common pattern would be like you could only save at certain points in the game, and often I mean like you go into a room and then like you only load the map of the one room and then you save, and that's fine. But Crash Bandicoot just had this like weird save point design. So in any one of the levels, you had to accumulate 3 tokens, and they were always hidden somewhere in the level. And then once you got the 3 tokens, I was like, okay, great. Doesn't mean you can save. It means you have the right to go to a bonus round, and then you have to clear the bonus round, and then at the end of the bonus round you could save. But you could die when you were collecting the tokens, and you could also die in the bonus round, at which point you wouldn't be able to save anymore. So that's pretty crazy, right? Like that's weird design. But this is kind of what we do to our own brains every time we load tons and tons of context without any kind of safety harness. So this is a comic I found from monkeyyuser.com. Like I think we can relate to this a little bit, right? Like someone comes and taps you on the shoulder after you've been, I don't know, like reasoning about the state of your Kubernetes clusters for an afternoon. You're like, ah. So TDD gives you save points, more frequent save points when you're developing software. So why should we care about this? Or like, why do we care about this kind of context going poof? I have 2 ideas here. So this is a comic I drew last week. I'll read it out loud. So this was actually me when I joined my last team. So all I need to be productive on this team is I need to learn the language. Okay, gotta learn Go. Gotta learn the framework and the business domain and all the design decisions that Topher made before I joined. Just kidding. And I now need to like learn Kubernetes. So I don't know. Like I saw a picture of a full stack developer yesterday, and they like drew the stack went like completely off the screen. So the point here is that we're constantly juggling a massive amount of context when we set out to do even a small thing with code. And even if you're not this new person to a team, even if you've been working on a team for a while, the systems that we're building now are just getting bigger and more complex. So I find myself coming back to the Woods theorem a lot, which states that as the complexity of a system increases, the accuracy of any single agent's own model of that system decreases rapidly. And this is from Dr. David Woods. So we all probably know from some experience that when you set out to do just like a one-line change, it's frequently not just a one-line change, right? And if you think it is, maybe go ask someone who's a site reliability engineer, like, oh, can I just make one little change on a Friday afternoon? So TDD gives you save points. So when we start thinking in too many threads, like holding too much context, TDD helps us reduce the scope of the context that we have to hold. By working one failing test at a time, TDD helps you to restrict the number of open questions at any given point in time. So if someone comes and taps you on the shoulder, it's fine. You got a failing test in front of you. You remind yourself where you were. So the summary of this portion is that test-driven development is for humans. It's not for the machine. Having the artifacts generated for test coverage and verifiability and regression prevention is a nice to have, but I fundamentally think that test-driven development is about the process of designing and reasoning about software. So the final part of this talk is how can test-driven development improve software design? So what are like the external, this picture has nothing to do with the text. I just like threw random stuff on there. So TDD can also improve software design and help us be agile. So when we use failing tests to drive implementation, it means that we're constantly thinking first about how do I test this thing, rather than how do I write this thing. Code that's testable will have some nice side effects, as I mentioned earlier. Oh, this has some nice side effects. So hopefully, like, we all sort of know what interfaces are in Go. Interfaces represent a collection of behaviors that the collaborating modules, like collaborators, depend on. When we use test-driven development, we can actually incrementally build up and verify interfaces. So we can also sort of keep an eye on how big, like small interfaces are good in Go. If your test suite is getting really, really long, that's another signal that, maybe make your interfaces smaller. But in this little toy example, imagine that you have a function that depends on, you have hello that depends on a speaker to speak. So the collaborator can be any type, doesn't really matter, as long as it implements the speaker interface, right? So how can we test this? So you can write a test that makes an assertion on the main function under test. So our current system under test is the hello function. We're not really trying to test the speaker right now. We can actually pass in a fake version of the speaker. So Go interfaces, right? Like Go doesn't care what the type of the speaker actually is under the hood. Go also doesn't care how you implement the speak function. Go only cares that it's implemented. And of course, the nice thing about, so this fact gives us a lot of freedom when we're designing for testability. Freedom to, for example, invent a fake speaker that tracks its own call count and can tell the developer, hey, I was called. But at that point, we don't really care what happens in reality. So interfaces and fake implementations of those interfaces help you focus on developing only one module at a time. And I use the word module here kind of loosely, like one component at a time, whatever, like the system under test. The benefit of here is that you can keep extending the interface as you need, and you can keep building layers of verifiability at these component interaction boundaries. So this results in, I think, in more strongly defined modularity in packages that have stronger opinions about what they're actually meant to do. So when you have a lot of modules that kind of know about each other's business, but they don't directly interact with each other, this is really, really useful because sort of putting a shim at those borders prevents you from going down a rabbit hole, like, say, okay, if like the Anna module in the middle here called Elsa, and Elsa then goes and talks to Glaceon. You can't really see my mouse pointer, but that's what they're meant to be. Then we don't actually care what, so like Elsa's the blue one. If you haven't seen Frozen, Anna's the one in the middle, Elsa's the blonde one, Olaf is a snowman. So Anna's friends are Olaf and Elsa, right? But beyond that, Anna doesn't care who they talk to. So you can model that using interfaces and fake implementations in Go testing. It's like, that transition worked, it's fine. So let's put it all together, right? So if you want to roll your own fake interfaces, fake implementations, this is about the total amount of code you would have to write, of course, in a toy example. But the point here is that the more that you can be aggressive about reducing the surface area of your testing and being disciplined about what it is that your system under test is, the more that you can reason, the more effectively you can reason about what's actually going on. And I think you'll find that you will go faster in the long term. So some of you might be looking at this and being like, I don't want to make fake speakers all the time. That's so annoying. Like, it'd be like writing if error doesn't equal nil, like 10 million times day to day. So the good news is that there are libraries for this. The library that we use is Counterfeiter. We use this all the time. You can look into this library, which, as long as you define an interface, you just put a little annotation on top of the interface, and it will automatically generate for you a whole bunch of stubs, like fake methods, I guess. I don't really know how to describe. I'll show you an example in a second. So this is from the Concourse code base. In this case, we have an interface called notifications, and it just does two things. It listens and unlistens. So a nice small interface. So if we look at the test here, there's a collaborator, that's the one that's actually under test. When we call the fake notification, which is generated from, this is an instance, I never know what the term for that, of the fake implementation. In the before block here, we swoop in and we say, okay, when you get called listen, don't actually do what you were meant to do. Instead, return nil as the first argument, return a new error as the second argument, which allows us to write a really short and concise expect assertion. So Counterfeiter, super, super useful. It's really well documented. Definitely check it out if you're interested in exploring this. So the final thing I'll really quickly cover is another way that driving up behavior with tests helps guide us towards better design is, I think sometimes it's really easy and it's really tempting to write code that works but isn't really testable. So I think the prime suspect for this is when you have global state changes or when you have implicit side effects. So in Golang, you often can't assert state changes happening in other libraries because you don't have access to internals, you can't really reflect your way into the format package, things like that. But beyond that, it's just kind of dirty. It breaks encapsulation, and we shouldn't really do this. So when you start designing your code so that your inputs and outputs are super, super explicit so that you can test them, I think you'll also end up designing for readability. So there's a name for this pattern, actually. It's called dependency injection. We already do it all the time in object-oriented programming, and I know Go is not like an OO language, but it's fine. We can still take some of the good parts of object-oriented programming and learn from it in Go. So in more toy examples, this is an example taken from the book Learn Go with Tests. So imagine you're asserting a side effect to an output, like a buffer or something, such as standard out. Consider, what if you pass the entire buffer into the argument rather than just calling format.println globally, or what is it, printf. So this is pretty similar to the last example that I showed you, but the thing I want to call out here is that you can inject anything, and you can inject things that are maybe global, or maybe previously were global. So in this case, it might be a logger, it might be a config JSON that you make some assertions against, but in other cases, in totally separate examples, you can inject things like time. You can inject the time package, you can inject channels and inspect what's actually happening in your Go routines. You can do lots and lots of really trippy things when you start making things super, super explicit. So here's some more resources. Don't worry about screenshotting this. I'll post, the slides are actually already online. So yeah, I really recommend checking out that ebook, Learn Go with Tests, if you're new to this. It's got really great walkthroughs. My friend Chris wrote it, so I have to say good things about it. So yeah, my slides are there. Thank you. You've been an utterly great audience.